Good morning, Panthers. Today we are going to talk about oxidation-reduction reactions, also sometimes known as redox reactions. And this is going to cover chapter 5.9 intro, specifically dealing with oxidation-reduction reactions. If you want to think of what oxidation-reduction reactions are, they are electron exchange reactions. They're an exchange of electrons between one species and another. One is oxidized. That's the one that loses electrons. We call that oxidized. And the one that gains electrons is called reduction. And some of you may have heard some little mnemonic tricks like oil rig, oxidation is loss, reduction is gain, or Leo says Gur is another one that sometimes people have heard, lose electrons, oxidized, gain electrons, reduced. I'm going to show you that little trick, while it does tell you what is happening with the electrons, is actually quite difficult to use with just looking at an equation. So we're going to spend time on learning how to assign what are called oxidation numbers, which is kind of basically an electron bookkeeping trick, and using those oxidation numbers to determine which reactant is oxidized or which one's reduced, and hence which one's the oxidizing agent and the reducing agent. So let me just quickly recap our prior videos. We mentioned that there are three major classes of reactions. There's precipitation reactions, and these are characterized by a solid being formed on the product side. And I should just warn you that just because you see a product on the product side does not mean it's a precipitation reaction. You have to have a few other things. A solid has to be formed, but also you need to, it's an exchange reaction. So you have to exchange the cations and the anions. And in order to write your products, you would have switched the cations and the anions to produce your product. And then the last thing you need is to use the solubility rules to figure out which one has formed the solid. So precipitation reaction is an exchange reaction. You exchange the ions. You need the solubility rules. And then if a solid is formed, you can determine that it is a precipitation reaction. Second major class of reaction is an acid-base reaction. And the general formula for that is acid plus base yields salt plus water. This is also an exchange reaction. You're going to exchange the anion and the cation from this. And if you form water as one of your products and you form an ionic compound as the other, that's kind of a giveaway that it's an acid-base type reaction. And the third type of reaction is the one we're dealing with today, and that is an oxidation-reduction reaction. And I've already mentioned that this is an electron exchange reaction. And there's a couple of things we're looking for. The first thing we're looking for is, and actually the key thing we're looking for is, we are looking for a change in oxidation number. So once I show you how to figure out oxidation numbers, if you can identify a species that has changed in oxidation number, then you are pretty confident that you have an oxidation-reduction reaction. In fact, you do have an oxidation-reduction reaction. A couple other things I'd like to say about this. If you identify something as being oxidized, then something must be reduced. So if you have something that's oxidized, there has to be a corresponding reduction. In other words, because of this electron exchange business, one of the electrons, oxidation is losing electrons. So one species has to be losing electrons and another one has to be picking them up, gaining them. That's the one that's reduced. Okay, so let's take a look at how we can use oxidation numbers. First, let's define what oxidation numbers are, and then let's take a look at how we can use oxidation numbers to determine whether a reactant is oxidized or reduced in a chemical equation. So this is from a different textbook, and these are a list of oxidation numbers. This is not a complete list of oxidation numbers. And this is the periodic table, obviously, and these are different potential oxidation numbers that can be assigned to each of these elements. And what I would like you to conclude from this is, there is no way I could memorize all this. And I know there are certain biology majors out there that love memorizing things and think, I can certainly handle that. I would not recommend you try to memorize this. There's just too many exceptions. If you look at some of these elements in the transition metals, it's got 5 or 6 possible oxidation numbers. Chlorine has 6 or so oxidation numbers. Nitrogen has a ton of oxidation numbers. So memorizing this table would not be a terribly good strategy. I mean, you've got a few things that only occur as one oxidation state, like aluminum, all the group 1 cations, most of the group 1 cations, all the group 2 cations. So there are some, but I would not recommend that you use memorizing this table as a rule for you. So what's a better way to deal with this? I'm going to start by writing out a chemical reaction that is a redox reaction. So we have zinc metal and hydrochloric acid react together to form zinc chloride plus hydrogen gas. Now, I think some of you may have done this in a lab. You take a piece of metal, you put a acid on it, and you'll start seeing some bubbles forming. That's the hydrogen gas, and then there's a corresponding salt that's also formed. Okay, so this is an oxidation-reduction reaction, and one of the dead giveaways for an oxidation-reduction reaction, if you ever see this in an equation, if you see something that's like an element all by itself and then it's combined in another form on the other side of the equation, that's a dead giveaway that it's a redox reaction. So actually we have two examples of this, hydrogen gas and HCl. Those have obviously changed, and zinc metal to zinc chloride. So if you see a situation where you have something in its elemental form and then it changes on the other side of the reaction, that's a dead giveaway, it's a redox reaction. Not all redox reactions are in this form, but if you see that, you know it's a redox reaction. So I want to use this example to show how we can assign oxidation numbers to different species. There's a set of rules we can follow to assign oxidation numbers to their elements. So rule number one is if you see something in the free element form, in other words, not bonded to something else, it can only be bonded to itself. So an example of this actually from above would be like zinc, H2 would be another example, O2 would be another example, Cl2 would be another example, aluminum, metal, gold, etc. You see an element in its free element form, the oxidation number is equal to 0. It's been assigned equal to 0. So using this problem above, we can say that zinc has an oxidation number of 0, and we can say that hydrogen has an oxidation number of 0. All right, that's the first rule. Second rule is that monoatomic ions the oxidation number is equal to the charge on the ion. All right, so if we have a compound that is a monoatomic ion and we can identify what the charge state is, we can figure out what the oxidation number is. So something like NaCl, those are both monoatomic ions. We know that sodium is a +1 ion. We also know that chlorine is a -1 ion. So the oxidation number of sodium is +1, and the oxidation number of chlorine is -1. Or something like, let's say, calcium oxide. So those are monoatomic ions. We know that the charge on a calcium is +2. We know that an oxygen is -2. So this one must be a +2 oxidation number, and oxygen must be a -2 oxidation number. Quick note here. If you've paid attention to these videos, you've noticed whenever I've written an ion charge for something that's not plus or -1, I've always written 2+ or 2- or aluminum 3+ or something like that. And that is in order to distinguish between the charge on the ion and the oxidation number. We use +2 for oxidation numbers. We would say 2+ or 2- for the charge on an ion. If I was writing out a phosphate ion, I would say something like PO4 3-, not -3, and that is to distinguish it from these oxidation numbers. Okay, rule number 3. Couple of ones that are always a certain assignment. So group 1 cations, these are always +1. Group 2, always +2. That should be a 4, shouldn't it? 5, aluminum, always +3. Fluorine, always -1. If you're trying to memorize a list of things, you might as well start with the things that don't have any exceptions. Okay, so group 1, group 2, aluminum, fluorine, those are always assigned certain numbers. Now, here's where it starts getting a little bit tricky, and I'm going to make the screen a little bit smaller here, and we're going to move over here. So number 7, oxygen is usually -2. There is an exception to this. Peroxides are -1. But generally speaking, oxygen is -2. Okay, so most of the time you can get away with assuming that oxygen is going to be -2, and if you see a problem that I'm going to give you, it's going to be a -2. It's not going to be an exception unless it tells you specifically it's a peroxide. Number 8, hydrogen is usually +1. There are exceptions. They're called metal hydrides. Those are very rare, and those are -1. But I would never give you a case where hydrogen was a metal hydride. So if you get to this level, you can actually assign oxidation numbers to most things. You've got all these elements that have always a certain value. You've got oxygen, which is usually -2. You've got hydrogen, which is usually +1. Now we can start assigning oxidation numbers. And then there's 2 more factors which are important. And I'm going to actually change colors on these just so you're highlighted for them. One, neutral molecules. Neutral molecules, the sum of the oxidation numbers has to equal to 0. If you add all the oxidation numbers on a neutral molecule, the sum of them is going to equal to 0. And for number 10, if we have a charged molecule, also known as a polyatomic ion, the sum of the oxidation numbers is equal to the charge on the ion. Okay? So we're going to do a couple of examples. I'm actually going to go back to this equation that we wrote up top, and I will show you how to assign some of these oxidation numbers. So the example we wrote on the top, we already figured out that zinc is a 0 because of rule number 1. It's a free element. We also figured out that hydrogen is a 0 because of rule number 1. Okay, so the oxidation number is assigned to 0. Remember, this is an electron bookkeeping trick. Okay, so we're just assigning these values, and I'll tell you why we're assigning them in a second. For now, we're just going to worry about how to assign them. All right, so HCl is the next one I want to deal with. And here's the way I like to do this. I like to pull the molecule out of the equation and say, all right, what are the oxidation numbers for this? So the first thing we want to note is, which of these cases would be true? Well, it's not a fluorine, and it is a hydrogen, so it's usually +1. But then I want to look at 9 and 10. These are the key ones. This is a compound, right? So it's a molecule of some sort, and it's either charged or neutral, but there's no charge up here, so this must be a neutral molecule. So what I know is, at the end of the day, the sum of the oxidation numbers has to equal to 0. So I like to create a little table, and I do something like this. I say this whole thing has to equal to 0. And then I look at the elements that are in here and I say, all right, which ones do I know something about? Well, I know something about hydrogen. I was already told that hydrogen is usually +1. So that one I'm going to assign a 1, and then because of the subscript here, I know that there's only one hydrogen. So here's the thing that students often misunderstand. The oxidation number is assigned to each individual atom. So since there's only one hydrogen atom, and I know that it's +1, it's going to contribute +1 to the overall contribution to the molecule. And because this has to equal to 0, this has to be a -1. And since there's only one chlorine, that means chlorine has to be -1. Now we also could use the rule of monoatomic ions, whatever the charge on the ion is. So we could have used this rule, or I'm showing you how to do this with neutral molecules. So therefore, at the end of the day, the oxidation number for hydrogen is +1. The oxidation number for chlorine is -1. All right, so I'm going to write that up here. +1, -1. And now I'm going to erase this that I just did here, and I'm going to replace this with my zinc 2 chloride. I'm going to do the exact same strategy. Except this one's a little bit harder because I have 2 chlorines, not 1. And I just realized that I don't actually have this equation balanced. There should be a 2 out front of here, and I think that will balance it. But that 2 in front does not change the oxidation number assignments. Okay, so zinc chloride has, it's not a charged species, it's a neutral molecule. There's no charge on it. So therefore, the sum of these has to equal to 0. And I don't know what chlorine is necessarily, but I do know what zinc is. And how do I know what zinc is? Well, I know that has to be a +2 charge. Otherwise, that subscript 2 would not have ended up there. Chlorine's always a -1 charge. Therefore, the zinc must be a +2 charge. So I know that the ion charge is 2+, and I know that the ion charge of this is -1. So because this is a monoatomic ion, zinc is a monoatomic ion, the charge on the ion is the same as the oxidation number. So this has to be a +2 oxidation number. And I know there's only one of them, so it's contributing +2. The zincs are contributing +2. This has to be -2 in order for the sums of these to be 0. So that tells me, since there are 2 chlorine atoms, each individual one must be -1. 2 times -1 will give me -2. So therefore, my oxidation numbers for this are +2 for the zinc and -1 for the chlorine. Okay? That's how we assign oxidation numbers. All right, part 2 of this video, we're going to give you a chance to practice more oxidation numbers, and then I'm going to explain to you how you can use these to figure out which species is oxidized and which one is reduced.